Mr. Benson here with a video explaining the solutions to the second test. Starting off with the distance question. So remember, distance is the area under the graph, but it doesn't matter whether it's above or below the axis. So all we've got to do is divide our graph up into sensible shapes. So I generally go with triangles and rectangles, work out our area there. So we've got a half of 5 times 15 for our first triangle, plus 5 by 15. Again, half of 5 times 15 for the two triangles here in the center. Then we've got 13 times 15 as our final area. That adds up to 345 meters of our distance. Then we go to displacement. Now displacement is when we take into account that the area below the axis is a negative value. So displacement is going to be, so our first few polygons, so this is our 5 times 15 plus 5 times 15, so that was our first triangle and then our first rectangle. Now the two small triangles in the middle cancel each other out, so this is effectively our negative area, plus all that's remaining is the 13 times 15 as our positive area, and we end up with 82.5 meters of displacement. The acceleration of the toy car at 4.3 seconds. Now, what you've got to remember here is that the acceleration is the gradient. So all we've got to do is find the gradient at that point. Now, this is the point where we are going from 0 to minus 15 meters per second. So we've got our change in y over our change in x, or our change in velocity over our change in time. Minus 15 over 5 is minus 3 meters per second squared. Same deal for the next question. Now in this case it is accelerating, so it's not one of the sections where the gradient is 0 and so the acceleration is 0, so we just do the same calculation. Now it doesn't matter if you do from the axis to the maximum or from the minimum to the maximum, just as long as you get your time right. So we've got 15 over 2.5, which is 6 meters per second squared. Then sketching the acceleration graph. Now, whenever you're sketching a graph, you've got to make sure that you label it properly. So we've got to have our axes. So we've got our acceleration axis, and the units are meters per second squared. Then we're going to have our time axis across here. Now, sorry, you should actually try and draw straight lines. Time is going to be in seconds. Now, we know that for the first 5 seconds we were at minus 3, so we just show that we have a constant minus 3 acceleration for that first 5-second period, so that's up to 5 seconds there. Then at 10 seconds we go up to a positive 6 meters per second squared acceleration for 5 seconds. So this is 6 up here, and then that drops back down to 0, and the rest of the graph is at 0. So what I'm really looking for here is the axes, the labels and the units on both. You should put values on the scale that actually allow you to understand what values the graph is showing, and then obviously the graph being drawn correctly. Okay, a ball is dropped from a helicopter and falls for 7 seconds. How far does it fall? So this is basic straight line motion. All you've got to think about is what you know. Now, if it's dropped, u is 0 meters per second. Acceleration is 9.8 meters per second squared. Now, that's going to be on your formula sheet. We're told that time is 7 seconds, and we want to find the displacement. So our equation there is s equals ut plus a half at squared. Now what often happens in these situations is that u is 0, so that term effectively disappears. All we're left with is a half of 9.8 times 7 squared, which is 240 meters. Now, the vertical motion of it falls as observed from the helicopter. Now, this is important because if we're thinking about the displacement versus time graph, at the start the displacement is 0, so relative to the helicopter. So what we're going to see is a graph that has a sort of a parabolic shape going up like that. Now, the velocity versus time graph, again, should start at 0. Now, because I've shown this graph as being positive, then it would make sense that my gradient of the velocity graph is going like that as well. There are probably some arguments about doing this either way. Now, the acceleration versus time graph, the main thing that I'm looking for here is that it is a constant value. Whether it's positive or negative, again, is kind of arguable. I would say because we've shown a positive gradient on the velocity graph, that the acceleration should have a positive value. Okay, moving on to the questions about forces. So we've got a ninja standing on a roof with an angle of 45. Now the first thing we've got to do is a force diagram. So we're just representing the forces. So all we have is our object. Now it doesn't matter what it is. Now there's a few different ways we can represent that, but obviously the first force that we've got to think about is weight, because that's going to be acting on anything. Now we know that the weight force can or will be split into different components. So there will be some of that force which is acting down the roof. Now, because they are at equilibrium, we know that they're standing still, there must be balancing forces. So there must be a frictional force acting up the other way. And the last force that we need to balance all this out is we need a reaction force, which has got to be perpendicular to the surface, because that's what reaction forces do. Now, I'd probably accept that diagram. It might be better, or another way you could do it certainly, is rather than showing the entire weight vector heading straight down, if you were to show the weight perpendicular vector, which is going at 90 degrees, because this weight vector here is actually the sum of this vector and this vector here anyway. I'm not really fussed either way. If you show me the 3 vectors above the roof and then one of the vectors in the roof, one of the 2 weight vectors below the surface, I'm happy with that. You've just got to be careful with what the question's asking. Okay, so the frictional force between the ninja's feet and the roof. Now, this goes back to the previous answer, that we know they're at equilibrium. So it means that the frictional force must be balancing or opposing the weight force. So basically the frictional force equals the parallel weight force. Now you should have on your cheat sheet that this is mg sine theta. So all we've got to do is plug in our values. So we know that our ninja is what did I say, that they were 75 kilos. So it's 75 kilos, 9.8 newtons per kilogram, sine 45 degrees, and we end up with 520 newtons. Now you've got to make sure that your calculator is set to degrees. That got lots of people. Then one of the ninja's feet is cut off. Now you're thinking about net forces here. So we've got a 520 newton force down the roof, and we've got only a 260 newton force up the roof. This gives us a net force of 260 newtons down. So then all we've got to think about is just A is the net force over the mass. So it is 260 newtons over 75 kilos, and we get 3.5 meters per second squared as acceleration. Now, if they're falling over, sliding to the edge of the roof, how fast will they be moving when they get to the edge? There they go. So we just have to think about what we know and what we want to find. So we know that the displacement is 15 meters. The acceleration that we've calculated previously is 3.5 meters per second squared. Now we know that they started at rest, so the initial velocity is 0, and we want to find v. So obviously from this one, the equation is v squared equals u squared plus 2as. Now again, this is one of these ones where u disappears. So we get v equals the square root of 2as which is the square root of 2 times 3.5 was A times 15, and we end up at 10.2 meters per second being the velocity they have when they set off the roof. Okay, with reference to Newton's laws, explain 3 important factors that are relevant to the performance of a racing car. Now, Newton's law questions are ones that you've got to think quite a bit about. So it's not just saying what Newton's laws are or describing something about a car, it's tying the ideas together. So what I'm looking for is any 3 answers here that are sensible and also relate to the performance of a racing car. So for example, I would go with low mass because we know that acceleration is force over mass. So as mass decreases, the acceleration increases. So this describes something about the car. So we described that we have low mass. It relates it to Newton's second law, and it explains that relationship. Okay, going on to momentum questions. Now, the first thing you got to be careful with a lot of these questions that I've given is your unit. So I would pretty much always try and change from kilometers per hour to meters per second as the first thing that you do. It won't always get you in trouble if you don't, but most of the time it will. Okay, so the first thing we've got to always think about is the initial momentum. Now, only one object is moving before, which is the 4,000 ton train. So that's 4 times 10 to the 6 kilos times 25 meters per second, and we get 1 times 10 to the power of 8 kilogram meters per second as the momentum. And then the velocity after the collision is just going to be P2, which is the same value, over M2. Now, in this case, the 2 trains have locked together, which is a fairly standard basic momentum question. And so you get 1 times 10 to the 8 over 6 times 10 to the 6. And this is 16.7 meters per second. Okay, so calculate the change in momentum of the large train. Now, you've got to remember that this is the same as the change in momentum of the small train. It's just that you would call one of them positive and one of them negative. Now, usually we're only caring about the magnitude anyway, so the negative and positive thing is not super important. So the delta P is just going to be mv for the small train. Now the small train was 2 times 10 to the 6 kilos, and it ended up going at 16.7 meters per second after the collision, and we ended up with 33.3 times 10 to the 6 kilogram meters per second there. So this is the increase in momentum of the small train, and it would be the decrease in momentum of the large train. Okay, now working out the average force. Now all we've got to remember that force is impulse over time, which is the same as the change in momentum over time. And so we've got 33.3 times 10 to the power of 6 over 0.1, or whatever time value you get. And we get 33.3 times 10 to the 7 newtons. Okay, is the collision elastic or inelastic? So we've got to compare kinetic energies. You must do the calculation here. So our kinetic energy before the collision was just the kinetic energy of the large train, which is 1.25 gigajoules times 10 to the 9 joules. Now our kinetic energy of our objects after the collision, so this is 6 times 10 to the 6 kilograms times 16.7 squared, and that's 8.3 times 10 to the 8 joules. Please excuse my messy writing. And so it's inelastic because these values are not equal, and specifically that EK2 is less than EK1. So this is a very standard Year 12 question. You've got to answer like that. Okay, then we get on to more straight line motion questions. Again, be careful that we are converting our values properly. So U is 110 kilometers an hour, over 3.6 is 31 meters per second. I'm just rounding stuff a bit here for ease of answering it. Now, before the brakes are applied, means there is no acceleration. So all we need to think about is just that S is ut. So it is just 30.6 times 0.5 seconds, and we've got, what's that, 15.3 meters that it's traveling before the brakes are applied. Now, during braking means the acceleration is actually non-zero. So S we're trying to find. Now U we know was 31 meters per second. V is going to be 0 because we want them to stop. And we know A is, what did we say that was, negative 11 meters per second squared. So then we've just got to put this into V squared equals U squared plus 2AS. Now you can substitute and rearrange, or you can rearrange and substitute. Now in this case V squared disappeared, so all we end up with is S equals minus U squared over 2A. So this is minus 31 squared over 2 times negative 11, and we end up with 42.4 meters. Okay, can they stop in time? So what you've got to think about is they're going to travel for about 15 meters before the brakes are on, and then 42 meters with the brakes are on. So S total is 57 meters, which is less than 60 meters, so they can stop. And so you would just need to express that in a reasonable sentence. Okay, getting on to our last couple of pages, the force versus displacement graph. Now this kind of question is also important to understand. Anything with a graph, you've got to remember that you can look at the area under the graph and it will tell you something. Now we're only interested in up to here, so this is just work is a half of 8 times 8, which is the area of the triangle. We get 32 joules. The final velocity of the object. Now again, we're talking about energy transformations here. So the assumption is that the kinetic energy equals the work, which is 32 joules. The velocity is root 2 of EK over m. Now this is a really useful relationship. If you can't remember how to rearrange the equations, make sure you have this on your cheat sheet because you'll use it a fair bit. So all we do there is 2 times 32 over, now the mass of our object was 10, and we end up at 2.5 meters per second as our velocity there. Okay, and last, they're more fairly straightforward, we've got just a kinetic energy and a power question. So again, get your units right. You can't do this if you're not in meters per second. You're definitely going to get the wrong values there. So 33.3 meters per second. EK is a half mv squared. So you've got to do this in meters per second. So I've got a half of 1400 times, and you've got to remember, this is the number one mistake, to actually square it, and we get 778 times 10 to the 3 joules or kilojoules. Power is just work over time, so it's the same as the kinetic energy over time. So we've gone from no kinetic energy to 778 times 10 to the 3 joules, and we're dividing that by 8.5, and we end up with 91.5 times 10 to the 3 watts. Okay, hopefully you found that helpful. Oh, no, sorry, I recall we are not actually finished. What I haven't covered here was the explanation of the torque question. Now I'm just going to mention it quickly. Most people are reasonably good at working out torque. You've just got to remember that you have to calculate a component that's actually perpendicular to the radius. But the number one mistake people made on the torque questions were you forgot that if you've got torques going on opposite sides, you've got to treat one of them as a positive value and one of them as a negative value. If you're not and so when you add them up, they're going to cancel out slightly. Now, if you're not sure what I mean by that, just ask me anytime this week before the test. There definitely will be talk questions on the test. The other thing is that the questions on the test are going to be slightly different to the ones you've done already, so you can't just assume that you completely know what you're doing. If you've done okay on the practice tests, you've got to make sure that you're practicing other questions as well.